Hello, everyone, and welcome to today's webinar in the CERDUP and ESTCP webinar series. My name is Rula Deeb. I'm a senior principal at Geosyntac Consultants in Oakland and the coordinator of the webinar series on behalf of CERDUP and ESTCP. It will be my pleasure to facilitate today's call. This event will consist of a brief overview of CERDUP and ESTCP by Dr. Andrea Lisa, followed by the technical portion of the webinar. Today, Dr. Michael Cavanaugh and Dr. Dave Reynolds from Geosyntac and Dr. Kevin Mumford from Queen's University will present their work on applying value of information concepts to site characterization and conceptual site model development with a focus on a framework for optimizing site characterization to minimize the cost of achieving remedial goals. We will pause roughly midway through their presentation for a short Q&A session, and we'll conclude the webinar with a longer interactive Q&A session with our three speakers. Today's broadcast will be listen only. In case of technical difficulties, please submit a chat for us in the chat box in your screen. If you're having problems with the browser, consider using another one. Firefox, IE, or Edge are most compatible with the network program that we're using. If you cannot see the screen, or if your screen freezes, key in Control plus F5 to do a hard refresh of your browser. If you cannot if you're trying to connect to the computer audio, click the arrow next to the Join Audio button. Select Test Speaker and Microphone and follow the prompts on your screen. And if you continue to experience difficulties, please consider calling into the conference line using one of the two phone numbers shown here, and please make sure to enter the required conference ID also shown on this slide. If you'd like to ask a question, please find the Q&A button on the control bar and type in your question or questions. Make sure to add your organization name at the end of your question so that we can identify you during our two Q&A sessions. It is now my pleasure to introduce Dr. Andrea Lisa, who is the Deputy Director of CERDUP and ESTCP and also the Program Manager for Environmental Restoration. Andrea has been with CERDUP and ESTCP since 2001. Before that, she served as a research scientist at Battelle, where she conducted research on in situ bioremediation and the design and implementation of innovative biological, chemical, and physical treatment technologies for site remediation and also industrial wastewater. Andrea received her doctoral degree in environmental engineering from the Johns Hopkins University. Andrea?
Thank you, Rula. So before we jump into the technical details of our webinar today, I'd like to talk a little bit about CERDUP and ESTCP and how we got to the webinars today. CERDUP and ESTCP are sister research and demonstration programs. We're the DoD's environmental technology programs. CERDUP is our science and technology program, and it's a partnership between DoD, DOE, and EPA. And most of the work we do here would be our R&D, often at the university level, with some research done also by military labs, federal facilities, etc. ESTCP is the partner program, and under this program, it's demonstration and validation, and generally what occurs is the knowledge or the technologies that are developed under CERDUP mature and essentially graduate into ESTCP, where they can be demonstrated and validated in the field. And very important to us under ESTCP is that technology transfer occurs from these technology demonstrations so that the information we're learning gets into the hands of the end users. Slide 10. Now we have a couple of broad categories of need that drive the type of research we end up funding. And what I'd like to do a little bit is introduce those to you. First is that we are working to sustain our testing and training ranges, as well as facilities and operations in a number of different areas. And as you can see from this slide, it's very broad what we're looking at, from maritime sustainability to noise issues, sustainable forward operating bases, UXO, and the munitions constituents associated with them. Slide 11. We also deal with reducing the current and future liability from operations on our military bases. So there we're dealing with essentially pollution prevention to control the life cycle costs of the various chemicals and processes that we need to use on our bases. And then we also deal with the contamination from past practices. And much of what we'll talk about today is dealing with contamination from past practices. Slide 12. And so, as I mentioned already, one of the most important things we deal with is technology transfer. And so we have a number of different mechanisms that we are using to try to get the information out to the appropriate communities. Slide 13. And this varies from videos, we have in-person training, we have an EnviroWiki on our website, various guidance and manuals. And then of course we are using webinars, and our webinars are a way that we have been promoting the technology once it's mature out to the end user audiences. Slide 14. Information about our CERTIP webinar is available on our website. On this slide, I'm just showing you a few of the webinars coming up, but you can see that there's quite a variety in the topics. Registration is available on our website. And then after the webinar, we also archive the information so that you can always go back and listen to the webinar later if there's something you missed, if you want to listen to it again. Registration for all of the webinars listed here is already available on our website. Slide 15 provides you the website here to go to directly to register for the webinar series. Slide 16. And then I'd also like to mention our CERTIP Symposium. The symposium is held annually at the end of November, the week after Thanksgiving. It is truly an excellent means to get information about all the projects we are funding and the different initiatives we're addressing under CERTIP and ESTCP. Registration is now open, and you can also see all the tech sessions that are being offered. But a big part of the symposium also is our poster session, and every project that we're funding presents a poster, and so you really get a good opportunity to see all the latest technology and knowledge coming out of the program. At this point, I'd like to turn it back to Rula, and we'll go into the technical part of our webinar, and I hope you enjoy it. Thank you.
Thank you so much, Andrea. I'm going to go ahead and introduce our three speakers for today before turning it over to them. Our first speaker will be Dr. Mike Cavanaugh. Mike is a senior principal with Geosyntac in Oakland, California. He is a registered professional engineer, a board-certified environmental engineer, a fellow of the Water Environment Federation, and also an elected member of the National Academy of Engineering. Mike has over 40 years of consulting experience advising private and public sector clients on water quality, water and wastewater treatment, and hazardous waste site remediation projects. He earned a bachelor's degree in chemical engineering from Stanford University, an MS degree in chemical engineering, and a doctorate in civil and environmental engineering, both from the University of California at Berkeley. Our second speaker will be Dr. Kevin Mumford, who is an associate professor in the Department of Civil Engineering at Queen's University in Canada. Kevin's research focuses on the study of multi-phase flow in porous media and its application to the remediation of non-aqueous phase liquids in soil and groundwater, with an emphasis on the behavior of gases in contaminated groundwater systems. Kevin received a bachelor's degree in environmental engineering and a master's degree in civil engineering from the University of Waterloo, and a doctorate in civil engineering from McMaster University. And finally, our third and last speaker is Dr. Dave Reynolds, who is a senior principal with Geosyntac in Ontario, Canada. Dave's current areas of research include value of information in site investigation and long-term management, electrokinetic applications to remediate low permeability soils, and treatment of dilute saline plumes. Dave has been both an academic and a consultant over the past 20 years. He is very active with ITRC and has led 5 CERDUP and ESTCP projects. Dave earned a bachelor's degree in geological engineering from the University of Waterloo and master's and doctoral degrees in environmental engineering from Queen's University. And with that, I would like to turn it over to Dr. Mike Cavanaugh. Mike?
Thank you, Rula. Appreciate the opportunity to present our findings on this diver project, the acronym that I'll explain in a moment. Kevin Mumford from Queens, Dave Reynolds from Geosyntec, and I are looking forward to comments and responses from some of the many participants. Takes a few minutes to get this all settled in terms of the control.
Mike, we're having difficulties hearing you.
There we go. I should be unmuted.
Yes, please proceed.
Okay, it's unmuted and we're ready to go.
Please go ahead, Mike.
Great. Took a while to get the system under control, so here we are. So again, we're looking forward to the opportunity to present our findings today, and let me go through quickly the outline of what we're going to cover. The problem we're addressing is a DNAPL issue. We're simulating a release of trichloroethylene as a DNAPL and looking at how best to conduct an investigation that would lead to a successful outcome and remediation performance. I'll give some background on how we organized our diver project to do a value of information type of assessment, looking first at how a site should be investigated, comparing the investigation undertaken by teams that we've organized, practicing teams who will then compare their results against what we have from our computer model, which we're defining as, quote, perfect information, and seeing how that can relate to effective practice in characterizing the sites, and how that information then can then be translated into an accurate conceptual site model that will lead to the best performance of the proposed remedial strategy. We're looking at only one technology, the enhanced in situ bioremediation technology, and we will then talk about some of the key conclusions that we've reached so far in our assessment. The team consists of a number of folks from Geosyntec. Dave Reynolds and I are the co-PIs in carrying out this work. We've been supported by a number of other folks. Some of the names are familiar to people on the call. Bernie Cooper and Kevin Mumford are the two co-PIs from Queens. And then we have Peter Kitanides, who is a geostatistical expert who's helped us with our optimization routines and assessment of the value of information approach. The problem definition then, as we all know, chlorinated solvents have been and continue to be a significant liability of a large share of the legacy problems of facing the Department of Defense. In all of these sites, we have experienced, of course, an adaptive management approach, a phased approach to characterizing a site. And at various decision points in the life cycle of a site, one needs to decide on what level of additional effort is needed, and that investigation may increase or decrease the cost of the remedy. One hopes that it will normally lead to a decrease, which is not always the case. And this is a classic value of information problem, which was articulated in the 1990s by Al Fries and his colleagues in 4 classic papers in the journal Groundwater. And that particular approach has not gotten a lot of traction in the remediation world, in our opinion. in part because of the difficulty of predicting outcomes based on new information. And so we postulated in setting up this project that new decision tools are needed to help make these decisions at any point in the life cycle of a contaminated site. Now, to put this into some quantitative characterization, you see that the DoD has a goal of 95% remedy complete by 2021. They're reporting about 85% complete as of 2016, with some funding set up for 2018. We think this likely underestimates the cost for mega sites and some of these large complex sites where the trying to get to the goal of unlimited use and unrestricted exposure, the so-called restoration goal, presents a continuing challenge and one that demands a characterization of the potential risks associated with not being able to reach that goal in a reasonable time frame. The megasite problem, of course, does not mean restoration, and as many of you know, even a delisted site off of an NPL list does not necessarily mean restoration. It often means long-term management. And at various moments in the life cycle of the site, particularly at complex DoD sites, which dominate the budgeting area, one needs to consider whether a transition to some long-term management or institutional control decision is desirable and can be justified. So one of the key issues then is what additional information is needed that would address the risks of residual contamination. This is a classic geotechnical problem in terms of implementing a remedy or a institutional control that limits the probability of failure and the consequences of that failure. So we're looking at the driver of information to carry out this analysis. And the question we posed was, how do we improve the return on investment in site investigation, leading to more efficient and cost-effective outcomes? Our acronym here, Data Information Value to Evaluate Remediation, DIVER, is an acronym to highlight the importance of a value information based approach in developing accurate conceptual site models and remediation decisions. We essentially are talking about how accurate does your conceptual site model need to be? How close is close enough? And we chose an approach which we think is unique, and that is we wanted to compare how experienced practitioners would perform compared to a stochastic and computerized approach based on perfect information generated by our computer model that we'll explain in a minute. The analogy I've used to try to explain what we're trying to do comes out of Malcolm Gladwell's book, Blink, where the Department of Defense hired a veteran to fight against computers in a simulated war exercise, and the practitioner easily defeated the computers. And so we're going to see how this plays out in terms of practitioners working against, in this case, perfect information as generated by our computer model. To put this in some graphical terms, as I think everyone agrees, usually investing more money in the site will reduce the level of uncertainty. And we're looking to take the red line, which is what we would call standard practice in terms of what kind of reduction in uncertainty you get for dollars invested, and bringing it down to the green line where you're getting a greater reduction in uncertainty, essentially more bang for your buck, and ultimately, hopefully, leading to a more cost-effective solution as you approach your remedial goals. So we're trying to maximize the likelihood of successful remedial strategies by identifying essentially what is the most effective practice for various metrics that we'll talk about in characterizing a site. We think that this will provide some significant benefits to DoD in terms of guidance on effective practice, identifying the most critical parameters that must be accurately characterized. This provides a scientifically sound and cost-effective approach, we think, to addressing the significant degree of heterogeneity that we face in carrying out remedial design and operation of in situ remedies. We want to identify what are the most valuable data parameters that need to be identified and characterized. And this analysis, the value of information type analysis, will be a critical component of deciding what to do at various key phases of a site life cycle. We also want to highlight in our analysis some of the limitations of different modeling approaches and assumptions that in some cases can lead to erroneous predictions of the future. With that, I'll turn it over to Kevin Mumford, who will talk about the first part of our discussion with respect to how we analyzed the site investigation in the virtual world. Kevin?
Great, thanks a lot, Mike. As Mike mentioned in his introduction, a large part of this project is really focused on that important question of trying to address how close is close enough, right? And this is tied into assessing the value of new information. It can help decide, directions to take in terms of value of information. But the reality is that this is a difficult thing to do because we just don't know what's in the subsurface, right? It's difficult to know how close you are to a target when that target is unknown, whether it is the extent of the plume or whether it's the quantity of DNAPL mass in the subsurface. That's a difficult thing to be able to evaluate. So to try to overcome that problem, we created sort of a kind of virtual reality. We created a series of virtual contaminated sites that you're going to hear me refer to as virtual site data sets, VSD-A, VSD-B, and VSD-C. So these are synthetically generated sites where we know all the information. We know the geology, we know the hydrogeology, and we know the various biogeochemical parameters at these sites. These sites were created using the numerical model DNAPL 3DRX. So that's a multi-flow simulator that in this case was used to simulate the distribution of both water and TCE to create a DNAPL source zone. That simulator is then able to model the dissolution and subsequent reactive transport of that TCE. So advection, dispersion, degradation to DCE and beyond, as well as sorption. And it can do that within a heterogeneous domain. So the figure that you see on the left-hand side is just an example of one of the plumes that we created after the dissolution of this synthetic source zone over time. You're looking only at the aqueous phase concentrations. It's a 5 ppb contour there as the outer edge. And you can see the implications of doing this within a heterogeneous domain. We see it here from a top view on the top, and then we have a vertical cross-section on the bottom. Now, all of this was done within reasonably large domains to add a sense of realism. So our numerical domains were between 300 and 500 meters in lateral extent. The figure on the left is only a portion of that in and around the vicinity of the plume. Despite the fact that they were large, they were simulated at high resolution, the kind of resolution that will allow us to simulate high-resolution site investigation tools. So the resolution that we used in these simulations is on the order of about 1 meter laterally and about 10 centimeters vertically. And all of this was done, as I mentioned, in a heterogeneous permeability field to give us that realistic plume shape. And then, of course, the output of those models gives us true values that we can use as comparison points. So we know the hydraulic head, we know water levels at every location in that model. We know the permeability, the hydraulic conductivity. We know the groundwater velocity anywhere that we want to look. We know the fraction of organic carbon to start making sorption calculations. We know the DNAPL saturation. We know dissolved concentrations throughout the domain. We know sorbed concentrations throughout the domain. So this represents a much, much higher level of perfect information than we'd ever see at a site, but allows us to make those comparisons between what you might get in investigation and what is actually there. In addition to the output from the model, we also situated these hypothetical sites in real locations across the United States. And we did this to provide realistic values of background concentrations. So we also know dissolved metal concentrations everywhere in the domain and major ions, the kind of thing that you'd get from a water quality analysis. Now, in addition to that kind of information, we also wanted to be able to represent background geochemical parameters, the kind of indirect indicators that you might want to use in a site investigation. And some of those examples are shown here on the left-hand side, and they provide those sort of indirect echoes of a contaminant plume, right? Things like ORP, things like dissolved oxygen, sulfate, hydrogen, methane, and so forth. And we developed a series of correlations to the plume data to allow us to simulate these indirect parameters. That means that all told, between model input and output parameters, background chemistry, and these biogeochemical parameters, at each one of our virtual sites, we have between 0.5 and 1 billion data values that represent our suite of perfect information. And the approach used in this project is to take that perfect information, and we have 3 versions of that, so VSD-A, VSD-B, and VSD-C, and enlist the help of investigation teams, right? Consulting teams made up of practitioners across the United States, and give them access to that data. Access not in being able to see it, but in being able to virtually investigate it. And I'll explain our virtual investigation tools here in a couple of minutes. So using that virtual investigation of our perfect data sets, those teams were asked to create a series of conceptual site models. And then, of course, we can evaluate their conceptual site models, assess them against the perfect data to try to determine how close they are. So this evaluation forms the first output of the Diver project, an evaluation of investigation tools and approaches used by these investigation teams in their investigation of our known perfect information. The second output from the Diver project also involves those teams, but is focused on remediation. And Dave's going to talk a little bit more about remediation towards the end of this presentation. But down the left-hand side of this figure, you see the investigation teams used the CSMs that they developed, and then they went on to design a remediation application, an EISB application, which we then also simulated to determine their performance. That was compared to the Diver team that also created a remedy, but they did it with an open book. They did it knowing that perfect information as a point of comparison to assess value of information. And as the last part of this, we actually compared that to a remedy design using the SEO toolkit. So a stochastic optimization process as a point of comparison against, as Mike said, the experienced practitioner. So the result of this is the second output from the Diver project, which is an evaluation of the remedies. But coming back to site investigation, which I'm going to talk about today, in addition to that output from the model, it was important that we designed a series of algorithms that could mimic real investigation tools. So we created these algorithms, right? Approaches that could take the input and output from the numerical model DNAPL 3DRX and turn it into measurements and formats that are representative of what you would get in the field. So we created virtual soil borings, virtual monitoring wells, CMT wells, MIP, DILIF. Teams could perform slug tests or pumping tests for hydraulic properties at these sites. We allowed them to collect groundwater samples or soil samples and perform virtual analyses on those to get concentrations. And we allowed them to conduct hydrophobic dye tests to look for NAPL indicators. So the example that you see on the left is just a virtual borehole log. So we can get soil type from the model. That's represented by a correlation to hydraulic conductivity, but you see it as a soil type. We have a PID trace in the middle of the diagram that you see there. For us, that's based on the total VOC concentration. And then, of course, we have observations from dye tests, which for us are based on DNAPL saturations. As a starting point for all of these investigation teams, we also created a hypothetical site history. We created a phase 1 report based on 4 to 8 monitoring wells at each of these sites to provide a little bit of a starting point. And then we enlisted the help of these investigation teams from the consulting sector, asked them to create these 3 CSMs using our virtual investigation tools and sample analyses to design an EISB strategy. Of course, through all of this, we also tracked their virtual costs. And then at the end, we compared the values from the team estimates to true values from our simulation across multiple metrics that are important for a CSM. So before we start looking at those results, just as a bit of a summary, there's a lot going on here. We have 4 teams that were enlisted to create these CSMs. I'll refer to them as teams 1, 2, 3, and 4. We have 3 virtual data sets. So sites VSD-A, VSD-B, and VSD-C, which we happen to hypothetically put in Springfield, Jackson, and Smithville. So all told, as a data set for us to draw from, we have 12 CSMs, the 4 teams across 3 sites. So before we take a look at how they did, let's take a look first at what they did. So as an example, we have here a stripped down version of one of our virtual site data sets. It happens to be VSDA. And what I've highlighted here is the extent of the site, about 1,600 feet, and the locations of the true DNAPL, footprint, and the true plume footprint. So these truths are only known to the diver team. They're not available to the investigation teams. And if we look at the first team, team number 1, we can take a look at what they did in terms of a site investigation strategy. You can see they used a lot of MIP. They were installed roughly in transects perpendicular to their estimated direction of groundwater flow, and they also installed a handful of monitoring wells throughout the plume. This is a reasonably typical approach. It was used by this team at a few other sites as well. What's not represented in this diagram is this was installed as a phased investigation. So you're looking here at tools installed over about 3 rounds of investigation. Let's take a look at what Team 2 did. Very different. In fact, quite incredible. This is a team that installed an irregular spaced MIP grid, very high density compared to the previous team. It was installed in an inside-out approach, and as a result, for example, I had to convince people that nobody knew where that true plume was, right? They seem to know where that green outline is. They followed up their MIP grid. They didn't, by the way. They followed up that MIP grid with orange boreholes that you see there in suspected source locations. Team 3, we see a different approach again. Wider spaced, also using MIP transects, but filling those in with CMT wells as well, and using a very high density of dilith to probe their suspected source zone. Finally, team number 4, similar to some other teams, irregular MIP grid installed in a phased approach, monitoring wells throughout the plume, but slightly different, a high density of boreholes to also probe that suspected source zone location. So even before we get into the metrics and how their estimates compare to the reality, we can start to draw conclusions just from their approach. We see that different strategies were used by the teams despite the fact that they're investigating the same site. In fact, we saw different strategies between the teams for a different site, but similar strategies between sites for a different team. So teams tended to do the same kinds of things, but different teams did different strategies. You can see here across a comparison of teams 1 through 4. So let's take a look at what kind of output this was able to yield based on the kinds of samples that they took. So we also see differences in the kinds of sampling that they conducted. For example, if we look at team number 3, a lot more groundwater VOC samples than other teams, an average of 67 samples per site. All these values are averages over all 3 sites that were investigated. And as you can imagine, they also installed a lot more wells, right? They have similar groundwater monitoring wells on the left-hand side, but a lot more CMT wells. We also see differences in the use of dilith, as you saw in the previous diagram, an average of 59 dilith locations per site. You also see differences here in the use of boreholes by the different teams, between 30 and 40 used by teams 3 and 4, compared to 8 to 14 used by teams 1 and 2. So we're seeing different strategies in terms of their locations, and we're seeing different strategies in terms of what they do at those locations. So let's take a look at the impact of those on metrics. So here we see average values for a handful of important metrics for a CSM. I've not divided this out between the different teams. This is all teams and all sites. And they've been ordered here from top to bottom, where the topmost metric, average groundwater velocity, had the best average score, and the lowest one here had the worst average score. The plot you're looking at, the x-axis, is the estimated value by the teams divided by the true value that we know from our perfect information. So in this plot, a value of 1 represents a perfect estimate. And we can see here there's quite a bit of spread, right? Not as much for average groundwater velocity. That was done reasonably well. But as we move down in that list, that spread continues to expand. And in fact, many of these estimates were not close to the truth. We saw 82% of estimates across all metrics, all sites, and all teams were within a factor of 10, so plus or minus 1 order of magnitude, but only 52% of the estimates were within a factor of 3. Let's take a look at the same data now, but slightly unfolded. So we now have more metrics on the left-hand side, including metrics for DCE as well as TCE, as well as having TCE mass discharge there at the bottom of the list. And we've unfolded it out to the right by team, because we can start to now, because there was different strategies for different teams, start to pick and choose elements of each strategy to try to assemble a collective notion of best practice. For example, we see here team number 2 had very accurate estimates for the top 3 metrics on this list, which are related to the plume. If you remember, team number 2 was the team that seemed to know where the plume was. They used irregular, high-density MIP placements installed in an inside-out approach. But it's not necessarily true that one strategy translates to success across all metrics, where we see this team did not enjoy as much success when looking at DNAPL mass or sorbed TCE mass. For those successful metrics, we may want to look at team number 4, which had the best average score for DNAPL mass. So we have the potential here that from all of these strategies to start picking and choosing to assemble some optimal combination. Now, we're not just interested, of course, in metrics like this, these quantified measurements. We're also interested in delineation. So footprint of both the DNAPL source and the plume is important. So here we see a plot again for just one of our 3 VSDs. What you see in green is the true plume footprint, and what you see in purple is the estimate created by each of these teams. The number in the bottom right-hand corner is a score that we created. To interpret that score, essentially know that a value of 0 means that they think the plume is everywhere. A value of 0 could also mean they think there's a plume nowhere, and a value of 1 means they got it perfectly. So those scores are reasonably high. Plumes were relatively well located. In fact, the score on the far right-hand side of 0.65 is the lowest of any site in any team. So that's actually pretty good. Despite the fact that we have different strategies, we seem to be able to find plumes well. That's not necessarily transferred to looking at DNAPL footprint. Here we see a mixture of successes, with some teams reasonably finding that footprint and other teams not doing as well. We see evidence of both overestimates and underestimates of DNAPL footprint, sometimes within the same site. And Dave's going to talk a little bit about some of the failure mechanisms that are involved in the image that you see here. Now, it's also important not just to look at these metrics and these footprints in isolation, but to also look at them in combination. For example, this plot now used to evaluate DNAPL shows how well they did in estimating the mass, which is on the y-axis, and how well teams did in estimating its location, its footprint, which is on the x-axis. And we see here the first observation: there is lots of scatter. Right? There's lots of variability in locating and quantifying DNAPL. But there are successes to pull out of this. If we remember team 3, which had DILIF that was used throughout this system, their 3 values here in blue are the closest to the true value, the perfect score of 1 and 1, which is represented by that black square. So team 3 is the only team with all 3 of their sites in the top 5. If we do the same thing and we look at DNAPL mass score, they didn't necessarily do as well. For DNAPL mass, we may want to look at the strategy employed by team number 4. We can also use this same strategy to look at the plume, which is shown here. Again, mass on the y-axis and plume footprint on the x-axis. And immediately we see that things look closer to the truth. We're generally better at finding and quantifying plumes than we are at finding and quantifying DNAPL. So there's some key points to close out from the site investigation portion of our talk. We see that different strategies were used by the different teams. Those strategies varied more between teams than they did between sites. and that what works for one aspect of a CSM, for example, plumes, may not work well for another, for example, DNAPL. We saw that most estimates, now that we have some idea of how close we're trying to get, most estimates were not accurate. 82% were within a factor of 10, and 52% were within a factor of 3. We saw that plume estimates were more accurate than DNAPL estimates, and we saw both overestimates and underestimates of the DNAPL footprint. Finally, and importantly, we saw that data analysis is just as important as data collection. Right? Higher accuracy in footprint, whether it be for the plume or the DNAPL, did not necessarily result in higher accuracy. It's just as important to know where to find your data as what to do with that data once it is collected. With that, that's the end of the site investigation portion of the webinar. I'll turn it back over to Rula to moderate a Q&A session before we keep going. Rula?
All right, thank you so much, Mike and Kevin. We are going to go ahead with a short Q&A session. As a reminder, you can submit questions using the Q&A box on your screen. We're going to go ahead and start off with a question received from Western Michigan University. And I think it's a question for you, Kevin. Did teams 2 and 4 assume that the source and plume were in the center of the grid?
The teams 2 and 4 assume that the plume was in the center of the grid. I doubt it. So I don't know that for sure. With all teams starting with the same CSM, or excuse me, with the same phase 1 report, they all knew that some of those wells had TCE in them, and they built out from those known locations. So not necessarily that it was in the center of the grid. Although the one image that I showed, I centered that image on the plume, but in the larger site, it wasn't necessarily in the center. They built off from known information.
Great, thank you. A second question from our audience. What was the basis for establishing a geological model for each virtual site?
Yeah, so to clarify, so none of these sites represent any particular known site. To build the geology, we used statistics from some of the most well-studied aquifers in North America. So we had a range of reasonable mean and variance of the log normal distribution of that hydraulic conductivity, and then we chose from those ranges to create these virtual sites. On top of that heterogeneity and based on the experience of the project team, we put in particular geologic characteristics, so clay layers, for example, to give us a range of complexity of that geology, right? So it's based on a collection of known statistics that are out there, as well as experience of the project team to create realistic but still fictitious sites.
Great, thank you so much. And this is a question from the state of Minnesota. And as a reminder to everyone, when you submit your question, please note your affiliation so that we can reference it during the Q&A session. So here's the question. Did the teams have a budget for their investigation?
Did we lose Kevin there? This is Mike.
Mike, do you want to answer the question?
Yeah, sure. I thought Kevin might jump in there on that one, but what we had was as noted, the teams could use various tools to investigate the site in as many phases as they wanted, and there were costs associated with the use of each one of the tools. So they were not given a fixed budget, but rather they were allowed to spend as much money as they thought was necessary to conduct their investigation. So there is a cost associated with each of those 4 teams. We haven't presented that, but that's going to be certainly part of the analysis of comparing the value of the information gathered. Team 3, for example, did spend more money than the others, but they got a better answer on some metrics of the analysis. So in any case, in response to the question directly, there was no fixed budget, and the issue was spend as much money as you want, recognizing that if you spend too much money, you're not going to show a good value of information outcome.
Thank you, Mike. And if we don't have Kevin, I'm going to ask you to also respond to this question. Did the team reach a conclusion on best practices regarding the sequence of applying investigation or investigative tools?
Yeah, I'm back, Rula. Thanks a lot. So that's a good question. We're working on best practice right now, but it's not so much around tool choice as it is around their entire procedure. So although I think we're tempted to think of what is the best tool to employ, that really isn't turning out to be the case, right? It's going to be the way in which a variety of tools can be used. So there's the flexibility there to choose the right tool for your particular site or your particular objectives, but there certainly appears to be a correct sequence to be able to do that. And that's largely, as we said at the end of that last slide, both a combination of where you install that tool and, importantly, what you do with the data afterwards. So this isn't just about finding things. This is about being able to do the calculations to be able to arrive at reasonable estimates of these metrics.
Great, thank you. All right. Which of the tools, in your opinion, and I'm sure Dave will talk about it later on, but can you elaborate on which tools provided the best value of information?
Yeah, so that's similar to the last question a little bit, where we're not seeing any one tool rise above all others. Dave is going to talk a little bit where we've seen some tools not being used the way in which they were intended, and as a result, you get quite low value for those. But for the tools that are used well, it's not so much tool by tool as it is the entire process combined. So we're not seeing one tool rise to the top as being the right way to do it.
All right. And another question from our audience. Did the field collection process eliminate field error? For example, was a sand always given to the team as a well-graded sand, or was it varied between poorly graded sand to silty sand? So how much did the laboratory results vary?
That's a good question. So we made a decision early on that what we wanted to focus on was variation due to the team's choices. So we did not install random error into our virtual analyses, whether that's geologic type, whether that's a chemical concentration, because we wanted to be able to interpret the results according to what the team choices were. Certainly in the field, you would see error of all different types, but we wanted to focus here on just one. With respect to the sand in particular, we actually binned the sand according to what the audience member's question was. So a well-graded sand was always reported as a well-graded sand, but we certainly had poorly graded sands that were always reported as poorly graded sands as well. So we had resolution in the geology, but we didn't have any error associated with the way that somebody may have reported that on a log.
Great, thank you. And a related question as far as hydrogeology, can you expand on the uniformity of the hydrogeologic information provided to the teams?
The uniformity. So we certainly worked hard to make sure that consistent information was given to all teams at the outset. So they were all provided with the same phase one to start. They were all provided with the same cost list. They were all given the same opportunities to install their tools. And as Mike said, they were given the freedom to spend the money that they decided to spend. So information was not shared between teams, but they all had the ability to request the same information.
Great. Thank you so much, Kevin and Mike. We got 3 questions on costs, so maybe we could save those to the end and get back in the final Q&A to some of the expenditures by each of the team as you make your comparisons. So at this point, we're going to turn it over to Dave Reynolds, who's going to walk us through some of the results. Dave?
Thank you, Rula. Where I'm going to take the remaining bit of this presentation is I'm going to dive a little bit deeper into what Kevin was talking about, the output number 1 of the Diver project. Specifically, I'm going to start looking at failure mechanisms, and my slides are not advancing.
Don't we all love new software? Give it 15 seconds, and if it doesn't work, we'll advance it for you, Dave.
Just have to be patient, Dave.
Yep. All right. There we go. There's my ugly mug. Let's think about root failure analysis. We saw from what Kevin presented that some of the teams had very accurate estimates on some of the CSM metrics, and some of the teams had less accurate estimates on the metrics in the CSM. So I'm going to focus on 2 and talk about 3. The first one is DNAPL footprint. We saw that 2 of the 4 teams had a very accurate estimate of the DNAPL footprint, and Team 1 and Team 4 in the earlier slide by Kevin had less accurate. And one of the underlying causes we found when digging into how they did their site investigation was the use of a MIP response correlated to indicate the presence of DNAPL. And so when teams used this approach, it resulted in a less accurate estimate of the metric. When we asked them to determine mass discharge from the source zone, we didn't talk about that too much. There was some very accurate answers and some less accurate answers. And the primary driver underlying the less accurate answers was simply using too few wells or not enough data. For example, one of the teams used a single well in the center line of the plume to estimate mass discharge within this fairly heterogeneous plume and permeability domain. And then if we look at DNAPL mass, one of the things we think is the key metric, particularly when going to a remedy design like EISB, again, the teams that used MIP response in some manner to estimate DNAPL mass tended to end up with far less accurate answers. And not only that, we also found there were a number of ways the teams used the data. So not collected the data or where they collected the data, but how they used the data. So there's 3 examples here. One of the teams, when producing their DNAPL mass estimate, assumed a DNAPL saturation of 10% throughout their entire DNAPL footprint. Another team, wherever a borehole indicated the presence of DNAPL, they assumed that the pore space was 100% filled with DNAPL, and that all of the pore space from that point halfway to the next clean point was filled with DNAPL. And the third one was that the DNAPL mass within the source zone was equal to the sum of dissolved and sorbed VOC concentrations. So we looked at this pretty hard and we thought, okay, when we're given access to perfect information, that allows us to look at many different ways of estimating these metrics and trying to figure out, is there a way that is uniformly accurate across the VSDs and then can be recommended as what we're calling effective practice. So we did this using the perfect information based on our personal experience at sites, as well as discussion with other practitioners at meetings, CERDIP meetings, etc. And to this point, we've developed this at what we're calling effective practice, not necessarily best practice, for 3 of our CSM metrics: DNAPL footprint, DNAPL mass, and mass flux. I'm going to talk about the first 2. It's going to start with DNAPL footprint. So the concept here is that old school is probably still the most effective way to identify DNAPL footprint. So the approach we took was to say, okay, adopt an outside-in approach, and we're going to identify parallel lines with equal spacing between those lines, and we're going to use some sort of tool, intrusive tool along those lines. That could be cores or dye testing or dye lift, whatever it is, that always assumes there are no false negatives, and then look at, all right, what's the effect of differing line spacing as well as differing borehole spacing in the identification of that DNAPL footprint. So a little bit of results here from effective practice. So we have 4 different pictures here. And what they do is so on the left, this is a very close spacing of both the lines that we're drilling holes on and the holes themselves. Grading across to the right, which is a very wide spacing. And the black numbers in the bottom right of the boxes are the scores, similar to what Kevin presented earlier. And then across the bottom is what would be the cost of this investigation. So this is labor, equipment rental, and analyses. So we see on the left, at a ridiculously non-realistic spacing of 5 feet, $10.4 million, you get very close to that perfect score of 1. And then we grade across to the right-hand side, which is a much wider spacing, cost of $195,000, and a DNAPL footprint score of 0.58. So if we compared this now to the team results, and you've seen this slide before, this is estimated DNAPL footprint versus real DNAPL footprint for teams 1 to 4. And specifically, I want to highlight what I've got circled here. So the top right effective practice at a reasonably moderate cost, gave us a score of 0.58. And if we compare that to the score for teams 1 and 4, which were the 2 least accurate estimates, we see that this effective practice approach provided a better, more accurate answer than the approach that was employed by those 2 DM teams. And my slide advance has stopped again. All right, there we go. Thank you, whoever fixed that for me. So I'm going to move on to the second metric, which is DNAPL mass. And again, the talking amongst practitioners and amongst ourselves, we went to, all right, is soil sampling and calculation of bulk retention an effective practice for estimating DNAPL mass? And you see in red there, a little bit of a spoiler alert, the answer is yes. So using this as an idea effective practice and using all that perfect information, we went and we did a stochastic approach. So you see in the figure, there is the red outline is the known information. And what we did, advanced slide please, was drill 1 borehole, do the bulk retention, estimate DNAPL mass. Drill 2 boreholes, do the bulk retention, estimate DNAPL mass. Drill 3, drill 4, drill 5, drill 6, and also every possible combination. So if you're drilling 4 boreholes, every possible combination of locations for those 4 boreholes. And you see the figure that popped up on the right, you would expect that as we increase the number of sample locations, we would begin to narrow down on a more accurate estimate of DNAPL mass. Advanced slide, please. So what we have here is a big cloud of data. And this represents the DNAPL mass estimate for each of those realizations of the stochastic approach. The vertical axis is the normalized DNAPL mass, so estimate over actual. So a value of 1 means that it has exactly estimated the DNAPL mass that's present. Across the bottom is the increasing volume of source zone. So as we move to the right, it indicates fewer numbers of samples. And next slide, please. So if we look at this and we look at, what would be reasonable to achieve? So these green lines represent a plus or minus 20% error in the estimation of DNAPL mass. Next slide. If we then narrowed it down further and we said, okay, now we're just going to put holes and sample for DNAPL on a regular grid, this narrows it down to their expectation would be, in most cases, we should be able to get within plus or minus 10%. Next slide, please. So if we look at comparing that to the team's estimates, and the blue dots you see are the same dots as you saw on the previous slides, the Y scale has just now been expanded out. And the purple squares indicate the DM team estimates normalized score. And as we can see, then the green lines represent that plus or minus 20%. And as we can see, none of the DM teams' estimates were within what we would consider as a reasonable estimate based on using effective practice across all 3 of our virtual sites. And then earlier, I highlighted some of the root failure analyses for the DNAPL mass, and these are indicated here. So the red circle is the team that correlated MIP response to DNAPL mass. The green circle is the data point where a uniform NAPL saturation was used, and the blue circle indicates the estimate where the sum of dissolved and sorbed masses was used. Next slide. So it's one of the questions that we're also trying to then, or we have to evaluate, is we've come up with these ideas for effective practice, and do they actually work? So we've done the stochastic analysis on perfect information. Now we needed to put it out to the practitioners. So we created another VSD, VSD-D, and we brought in 2 more teams for this. So we now have 6 teams, and we then gave the original 4 teams what we considered to be effective practice for those metrics, and allowed the 2 new teams to do whatever their personal preference or professional experience led them to want to do. So we look on this graph, and this is just for those 2 metrics I talked about, DNAPL mass and DNAPL footprint. The green vertical line, again, is the correct answer. The red diamonds are the old teams, original DM teams using the new effective practice, and the yellow diamonds are now the new teams doing what they wish. Now, we don't have all the data in on this yet, so there's just a few data points here, but preliminary is that we think we're seeing better results from the teams when they're using our proposed effective practice. Next slide. So that kind of ties up what we're going to present on the phase 1 site investigation work. There's a lot more coming on with that. There were a couple of questions in the first Q&A session about costs. We have tracked all of the costs for all of the teams, and we're going to be taking this to the next step, which is looking at accuracy or reduction of uncertainty versus cost tied in with effective practice to try and develop some guidance for input to decisions at site, where what tools in what way and what data analysis results in the most information for the smallest cost. But now I'm going to touch a little bit on remediation design. Next slide. So this was phase 2 of the diver projects. And you remember, as Kevin said, each of the teams was asked to take their conceptual site model and their estimate of what was going on at the site and design a bioremedy. And they were given some targets to achieve, as well as some guidelines for what they could do. So what we see in the table are, we gave the teams 3 targets: DNAPL mass removal, mass discharge reduction from the source zone, and an average concentration reduction in a plane down gradient of the source zone. And those targets changed a little bit between the 3 sites. We limited them to enhanced in situ bioremediation. We limited them to 5 years of active remediation. We then assessed these metrics 5 years later. And in this process, they were allowed 1 design change. So when they submitted their designs to us, they asked for a monitoring program. We provided that monitoring back to them at whatever interval they wanted, and they could use that information to redesign the system once. Next slide. So I'm going to just quickly present what the 4 teams did, 2 teams per page. So team 1, so in the black inset box, you see the actual DNAPL source zone. The red line is the team's CSM DNAPL source zone. On the left, where you see a pink colored dot, that's where they installed an injection well to inject lactate as an electron donor. And we see here with team 1, there's an alignment between where they put their injection wells and where they thought the DNAPL was. So there's a lot of injection wells and a lot of lactate injected down gradient into the plume that would not necessarily go towards achieving the metrics we asked them to achieve. Team 2, very accurate distribution or identification of DNAPL, but a very low, inaccurate estimation of DNAPL mass. 5 injection wells, and we'll see the results of that in a couple more slides. Next slide. Team 3, a little bit different. So they have all these black circles in the source zone indicate direct push. So their remedial method was to go in with direct push, do an initial injection of lactate throughout their source zone. Then they installed a number of up gradient injection wells to feed electron donor across the 5 years. Again, very accurate definition or identification of the NAPL source zone correlates to an accurate location of the injection wells. Team 4, very similar concept of focused injection wells where they thought the DNAPL was. The 6 pink dots that you see down gradient of the DNAPL source zone were from the redesign, where based on their results, they I don't know what was in their mind, but whether they thought they'd missed some DNAPL, perhaps. Next slide. So let's look at results. So the rows of this table, rows 2 through 4, are the 3 metrics that we asked them, that we evaluated their design and performance against with the goals. So numbers in green indicate that the team achieved the metric within the 10 years. Numbers in red indicate that the team did not achieve the metric within the 10 years. And on the far right column over there, we see the optimum, or the design by the diver team knowing perfect information. Across the bottom, we see the cost of the remedy, including installation, operation, electron donor, and monitoring. So we look at DM Team 1, the team that reached all 3 metrics had a total remedy cost of about $1.6 million. You compare that on the far right to the optimum design with perfect information was about $600,000. So Team 1 achieved the metrics at a reasonable cost, but in excess of what could be achieved with perfect information. Of course, we never have perfect information. We're never going to be able to achieve that $600,000. You look at teams 2, 3, and 4, varying degrees of success. Everyone managed to achieve the DNAPL mass removal, but no other team achieved the mass discharge reduction, and only one other team achieved the concentration reduction down gradient. Next slide. So kind of trying again to bring the initial results of this work for this one VSD together. And what we found interesting was we looked at, so the 4 rows of this column are the 4 teams. And the second column is the team's DNAPL mass score, so estimate over actual. The next column is using that estimated DNAPL mass, what would be the theoretical lactate mass required. The next column is the actual lactate mass added during the remediation. And the next column is the factor of safety, which is the lactate mass divided over the theoretical. And we see in each case, there's a significant factor of safety here that each of the teams used in terms of how much lactate they should have thought they may have needed based off of their conceptual site model DNAPL mass estimate, ranging from 28% up to 318% for team 1. Remember team 2 did not only achieved one metric, had a very low estimate of DNAPL mass, a score of 0.4. Even with that 55 times factor of safety, they did not achieve 2 of the 3 metrics. There's a column there which is DNAPL mass removed as a percentage estimate, and this was an interesting finding so this is how much DNAPL mass was removed compared to how much the teams thought was there originally, and whether that would have fed into a redesign decision or not. Next slide, please. So we're getting to the end, and trying to bring all of the information from this project together. That's the point we are now, and there is a lot of information. There's a lot of things to do, but I wanted to look at some high points or really high level findings that we are, and this goes to a question that was asked before, looking at prioritizing metrics. So rather than prioritizing tools, what was the most important thing to look for in terms of designing that remedy and increasing the chances of success? Figuring out what that is, DNAPL mass, DNAPL footprint, and then determining the appropriate level of investment. That's what we're right in the middle of now. Spending that $50,000 more in the site investigation stage, could that have saved $500,000 in the remediation stage? We've noticed that safety factors cannot overcome poor data interpretation or collection, but they are turning out to be a useful approach for considering value of information and risk. Next slide. So this is a graphic that the team has put together centered on this value of information question in the big blue circle. And next slide. The team has identified that there is value of information approaches that can be used within the site investigation, the design, and the remedy implementation phases. So the 3 stages of dealing with contaminated sites to get to achieving RAOs. The site investigation phase was the focus of today. Next slide, please. I talked a little bit about incorporating value of information into design. This is where we're finishing up this work now. Next slide. And then we're also now really looking at how do we tie value of information from those first 2 stages into an implementation, reduction in monitoring, reduction, starting to look at transition assessments to long-term management. Next slide. And so last slide of the talk, well, second last slide, sorry. How do we see that this work of the Diver project is going to be of value to DoD? And I talked a little bit about the transition point. What is sufficient characterization? Where should we be spending precious site investigation and monitoring dollars to help with that question? Starting to postulate on best practices for characterization and remediation, looking at life cycle savings, again, taking effective practices to mega sites that are going to be the ones that are left in the DoD portfolio. And then finally, how can we use all of this data and work that's been done, not just to help in site investigation, but also to help in training the next generation of scientists and engineers that are going to look at these sites. And next slide. So the ESTCP funded a spin-off project, if you will, from Diver, and it's called Tempo. And essentially what Tempo is the online version of Diver. So all of those VSDs are now contained in a web-based GUI where you can go in and you can perform site investigation in real time. receive exactly the same data that the teams received, use that data to develop your own estimate of the metrics, and then look at how well you scored, not only versus perfect information, but also versus all of the other people who are doing this. So all of the estimates from all of the users will be building a database over time. So the URL is here on the screen. It is, the site investigation has just come out of beta, so it is ready to go. There is a second long-term monitoring component of Tempo that we're still working on. Next slide. Rula, is it passing it over to you?
Yes, yes. And if you, our audience would like to get additional information about this project, you can visit the Certified ESTCP project landing page for copies of reports or related materials. So with that, we're going to transition to the second Q&A session. Please continue to input your questions in the Q&A box, but remember to please add your organization or affiliation. All right, so Dave, this is a question from the US EPA Superfund program, and it's related to the composition of the DM teams. The question is, if comprised primarily from the consulting community, did the teams entail senior, mid-career, or early career professionals, and did the PIs participate in the DM teams?
Good question. So just dealing with the second part first, none of the PIs were involved in the DM teams. They were entirely independent. And in terms of the DM teams themselves, the diver team, when we went out looking for teams to do this work, we approached the senior level practitioners and allowed them to decide how they wanted to do the work. So I'm not exactly sure of the distribution of the experience levels within each of the investigation teams.
Great, thank you. And we have a question from Bob Borden from Draper Aiden Associates related to the DNAPL mass present. Did it have a big impact on cost and performance as reported by the investigation teams?
So big is relative. I think there is absolutely understanding the DNAPL mass, where it comes into in a bioremedy is in the stoichiometry and in your electron donor addition. So if you were in a bioremedy and specifically within a given time frame, understanding your DNAPL mass to enable you to achieve enough electron donor or whatever amendment addition in the time frame would be important. I think Bob had a second question further down there. It's related to this about DNAPL footprint, which I would say is far more important when you're designing a bioremedy, and would also be more important when looking at other remedies, and particularly thinking about thermal, that if your expected DNAPL source zone is only 50% of the real DNAPL source zone, you're going to design and implement based on that, and you're going to have probably a significant failure of your remedy.
Thank you. And if you don't mind muting your phone while I'm asking the questions, is creating an echo, Dave. All right, another question related to the types of technologies that this could work for. So you only tested in situ biosimulation, or you only simulated that. Can the methodology you described be applied to any in situ technology?
So this is Mike Rula. I think the story, in our opinion, is any of the technologies that are traditionally considered for in situ use in dealing with the source zone, namely ISCO, ISCAR, thermal, in our case, EISB. We think that the approach will have applicability to any in situ technology because of similar kinds of value of information balances and trade-offs that have to be considered. So we think it's the methodology that we're going to finalize, and where you can see we're getting towards a conclusion on a number of different issues related to best practices. Those best practices will translate into the basis and the information needed to apply any technology.
Thank you, Mike. And maybe another question for you, if you can take a crack at it first, and then we'll open it up to Dave and Kevin. It is not clear how you will determine the value of information from the results of remediation performance results from the various teams. Could you please elaborate on that and on how you would account for a failure of the technology to achieve stringent targets?
Sure, that's a good question. The situation in a typical value of information story is to assess whether or not your proposed remedy will meet the goals. And if you don't meet the goals, there's a penalty that you would apply for the decision making. In other words, the greater the failure, the greater the penalty, and therefore you're driven to characterize the site more effectively to reduce that penalty. So the situation that we're looking at right now is to compare the various performances with the metrics we've used to the expenditures made by the teams in characterizing the site. So this is a key step in our final report that we haven't quite completed yet, but we will be showing and demonstrating that in some cases you can spend more money and not come up with the right answer, or your score is actually lower than you would expect with the expenditure. That would relate back to the use of the tools, how the tools were applied, how the tools were applied in sequence. So it's a much more complex balancing of factors than we, I think, anticipated initially when we started the project. So, but that's where we're going in a more classic value of information analysis. You would, when you deal with the failure piece, you increase the penalty that would be the consequence of your failure, and that would drive you, of course, to either invest more in the technology or more in the characterizing the site.
Great, thank you, Mike. And here's a question for the team from Texas Tech University, and maybe Dave can answer that one. Did effective approach training improve the team's performance compared to how they performed in the first round? Dave?
As I said, the jury's still out. We don't have all of that data in or processed yet. That was in the slide. So if you look at the spread of the metrics in the blue squares or the blue triangles, the spread was certainly smaller, but I will caveat that with there were fewer data points. So our gut feeling is yes, but we're still a little ways away from being able to be very confident in saying yes.
Thank you, Dave. Here's another question from Argonne National Laboratory. Can you discuss what the major cost drivers were for the investigation phase compared to the remediation phase? Dave?
Oh, that's a good question. Kevin, you're probably more familiar with the site investigation. Do you want to, and then I'll handle remediation?
Yeah, I mean, on the site investigation side, certainly the number of tools is a big driver, right? So those teams that chose a high density approach, they tended to have the higher costs, and I think that's reasonably known. The driver on that one, in terms of their motivation, we're trying to sort of unravel what was in their strategy. So the objective of finding the plume, and so I'm going to shoot from the hip here a little bit because I don't have the numbers in front of me, but the objective of finding the plume, that was not as high percentage of the cost as when they decided to go in and detail the source zone for those teams that chose to do that source zone investigation in a high density manner, right? So source zones are sort of driving that cost for those teams that spent a lot of money.
Great. Dave, would you like to add anything?
So on the remediation side, the most expensive remedy was, a lot of it was driven by the lactate mass that was injected. If you remember back to that table that I showed, you know, there was 250,000 kilograms of lactate that was added. So that was the biggest driver of their costs. The number of boreholes, you compare injection wells, comparing team 2 that only had 5 and a total cost of $500,000 to team 1 that had 27 maybe at a cost of $1.6 million.
Great. Thank you all. This was a very interesting webinar. At this point, I would like to remind everyone that both the audio and a copy of the presentation of today's session will be archived on our webinar webpage in case you would like to refer to them in the future. Our next webinar is on Thursday, November 1st, and it will feature Dr. Billy Johnson and Ms. Heidi Howard from the U.S. Army Engineer Research and Development Center. These two speakers will discuss their work on supporting DoD's installation sustainability through informed stormwater management. Registration is open for this webinar, so please visit the Startup and ESCCP webinar webpage to register for this and other 2018 webinars. Before we conclude, I would like to request your assistance in please taking a moment to complete the survey that will pop up on your screen at this time. This concludes today's webcast. Thank you so much for your time.